Hey everyone, welcome to this explainer. Today we are taking a seriously deep dive into the sheer physical forces of manufacturing. We're going to look at how humans have figured out how to permanently join solid materials together using, well, just brilliant observable physics. Let's completely shift our perspective on how the world around us is actually built.
Think of this as our very own industrial recipe book. We're going to quickly run through 5 key areas. First up, welding without the melt. Then, roll bonding, which is pure pressure. Third is ultrasonic welding, good vibrations. Fourth, friction welding, which is literally rubbing metal together. And finally, resistance welding, or the electric squeeze. Let's get into it.
All right, Section 1, welding without the melt. It's time to uncover the fundamental physics behind connecting metals. I want to kick things off by posing a bit of a mystery to you. How exactly do you permanently join 2 pieces of solid metal without melting them into a liquid pool? I mean, when most of us think of welding, right, we immediately picture flying sparks and metal turning into molten lava. But what if you need to join materials that would just be completely destroyed by that intense heat? Well, that's the journey from mystery to mastery that we're embarking on right now.
To really appreciate this, we need to draw a hard line between our 2 main categories. On one hand, you've got traditional fusion welding, which absolutely requires a molten, super high-heat liquid phase to mix the metals. But then you have the frankly brilliant approach we are exploring today, solid-state welding. With this lower heat process, the components stay completely solid throughout the entire operation. Zero liquid required. None.
Let's ground ourselves with a formal definition just to keep us focused. Solid-state welding is a joining process that takes place without any fusion at the interface of the 2 parts. But there's a major catch here, and I really want to emphasize this. For a strong bond to actually form, that interface has to be completely free of contaminants. We're talking oxide films, leftover metalworking fluids, even microscopic layers of gas. Cleanliness is literally the absolute key to making this work.
So, if we can't melt the metal, what's in our toolkit? Well, here are our clues. Solid-state bonding leans on one or more of these 3 exact parameters. First, heat, to increase the transfer of atoms. Second, pressure, to force the surfaces together and cause plastic deformation. And third, relative interfacial movements, basically shifting them around to disturb the interface and break up those stubborn oxide films we just talked about. That's the exact recipe you need to force atoms across the gap between 2 solids.
Before we dive into the specific techniques, I want to toss out some industrial terminology so you're fully equipped. Whenever we talk about the actual contacting surfaces of the 2 materials being joined, we call them the faying surfaces. Right, faying surfaces. Keep that in your back pocket, you're going to hear it a lot today, and it'll make you sound like a total manufacturing insider.
Moving right along to Section 2, roll bonding, pure pressure. Let's look at how sheer, unadulterated force gets the job done.
To anchor this whole abstract science thing to everyday life, let's talk about the change in your pocket. Take a standard US quarter. It's actually a composite metal made of cupronickel outer layers and a pure copper core. Now, to force these completely solid metal layers to permanently join, those metal strips are squeezed incredibly hard in a process called roll bonding. They undergo a massive 82% reduction in thickness. 82%! That is a ridiculous amount of pressure. And the mechanics are surprisingly straightforward. As the base metal and the cladding metal get squeezed between massive, heavy rolls, they're flattened out, reducing their thickness, which leads to a huge increase in the surface area between the layers. That sudden stretching of the surface, combined with the extreme pressure, actually forces the metals to chemically bond together through something called solid solubility. It's an incredibly powerful process used for everything from making coins to bimetallic thermostats. Okay, Section 3, ultrasonic welding, good vibrations. Here, we're swapping out those massive, crushing rollers for incredibly fast, microscopic movement.
Welcome to the wildly cool world of ultrasonic welding. The absolute heart of this process is a fascinating piece of equipment called a sonotrode. The word itself is a clever mashup of sonic and electrode. This transducer tip applies oscillating shearing stresses, basically vibrating back and forth, at mind-boggling frequencies, anywhere between 10 to 75 kilohertz. This insanely rapid shaking of the faying surfaces violently breaks up those oxide films, allowing the clean metals underneath to bond, and it does it all while keeping the heat well below the melting point.
What's really great is how versatile this process is. In one setup, you might see a stationary sonotrode tip being used for a quick lap weld, which is absolutely perfect for joining thin foils or delicate wires. But then you can swap that stationary tip out for a rotating disc. That gives you continuous ultrasonic seam welding. This is an absolute game changer for the packaging industry or assembling delicate consumer electronics where heat damage is just totally out of the question.
Moving into Section 4, friction welding, rubbing metal. Now, the crucial factor here is heat generation. It's exactly like rubbing your hands together on a really cold winter day, but scaled way, way up to extreme industrial speeds.
Let's walk through the intense timeline of a friction weld. First, you take a solid metal part, like a thick pipe or a solid bar, and spin it up to a staggering 15 meters per second. Second, you take a stationary piece and just smash it against the spinning one under high axial force. Third, all that friction creates immense heat. It softens the metal and violently pushes the contaminants outward into a ring, which we call a flash. Finally, you stop that rotation almost instantly, crank up the force, and those newly cleared, blazing hot surfaces fuse together flawlessly.
Now, let's cleanse our palate for a second. Friction welding is amazing, for sure, but it usually requires one of the parts to be perfectly round, so it can, actually spin. But ask yourself, what happens if, instead of spinning the parts themselves, we introduce a rapidly spinning third body right into the joint of two flat plates?
Well, the result is a relatively new, totally revolutionary process called friction stir welding. You use a massive multi-axis machine to plunge a spinning, non-consumable probe right into the seam. The friction heats the metal to about 260 degrees Celsius, so it softens it but definitely doesn't melt it. And it literally stirs the solid metals together, sort of like mixing dough. This technique is heavily utilized to build massive aircraft wings and aerospace components because it creates incredibly high-quality joints with virtually zero heat distortion. Finally, Section 5, resistance welding. Electric squeeze. So far, we've used pressure, vibration, and friction. Now let's introduce intense electrical current to the mix.
This is resistance spot welding, and it relies on a highly precise, computer-controlled four-step dance. Step 1. Copper electrodes clamp down on the metal sheets to apply mechanical force. Step 2. The system shoots a massive electrical current, sometimes up to 100,000 amps, which is just insane, straight through the metal. Because the fang surfaces actually resist the electricity, that resistance creates intense localized heat. Step 3. The current turns off, but the force stays firmly on to forge the bond. And Step 4. The force is released.
When you look at the aftermath, those 4 steps perfectly form a fully contained weld nugget right between the sheets. Because this process is so incredibly fast, highly automated, and doesn't need any extra filler material, this solid-state electrical squeeze is trusted to securely assemble millions of products every single day. We're talking everything from the muffler on your car to your favorite stainless steel cookware.
So, we've seen how squeezing, shaking, rubbing, and electrifying solid metal can create incredibly strong, permanent bonds without ever needing a melting pot. I want to leave you with this final provocative thought. If we can perfectly fuse metals while keeping them solid, pristine, and totally free of the distortions that come with melting, what impossible lightweight structures might we build next for deep space exploration? Thanks so much for focusing in with me today, and keep exploring the incredible physics that build our world.